Welcome to the session on analog electronic circuits. In this particular video, we are seeing the second application on diode. The first application being a clipping circuit, which we have already discussed the different type of clipping circuits, broadly classified into shunt clipping circuits and series clipping circuit. The second application, the widely used application, is a clamping network. Okay, in clamping network, where do we basically see it? Majority of our communication systems have a clamping network. What is clamping network doing? What is a clamping circuit basically doing? Clamping circuit is used to add DC levels to the AC input signal. I repeat, it is used to add DC levels to AC signals or AC input signal. We can also call the clampers like a DC converters or DC inserters or DC restorers, DC inserters or DC restorers. So in our curriculum, we are basically talking about the negative clamper and the positive clamper. The name itself is saying the circuit brings the entire AC signal. If this is my AC signal, correct, I am just writing a rough sketch here. If this is my AC signal, the negative clamper brings this entire AC networks below, or it pushes towards the negative direction. Okay, the entire waveform is pushed below, hence the name negative clamper. To what extent it is pushed, it will have a clamping level. So this clamping level will decide the level of clamping. Similarly, whenever I have the same input signal, and this input signal is pushed above some reference voltage, then we call the circuit to be a positive clamper. We can see we are pushing it towards a positive direction. So at what extent, it is decided by the reference voltage that you apply for the clamping. So here we have you can see whenever I was talking about a positive clamper, I am always referring to the negative peak. Similarly, whenever I spoke about the negative clamper, I am writing a threshold here. That means I am always talking about the positive peak. Simple hint, always the clamping voltage for a negative clamper is on the positive peak. I will repeat, the clamping voltage of a negative clamper is on positive peak. The clamping voltage for a positive clamper is on a negative peak. See, if I want to lift something up, I will hold the bottom part and lift it upwards, right? So I am moving it up, so it is a positive clamping. If I have to move the waveform below, I will basically hold the head of the waveform or the tip of the waveform, and I will try to push it down, correct? So I am moving it downwards, negative direction, hence negative clamper. What am I holding? I am holding a positive peak, hence I will always be looking at the positive peak whenever I redraw the waveform. For a better understanding, let us take one example. So I am taking an example of a negative clamping circuit. I have written a simple negative clamping circuit here, where I am applying a sinusoidal waveform at the input. I am calling the sinusoidal waveform as Vi. The clamping circuit has a capacitance and diode in the network. And to measure the output voltage, I am using the load resistance RL, across which I will be basically seeing V out. Okay, so basically we know for any capacitance we have a time constant τ, which is basically combination of R and C. R, I am writing it as RF, frequency dependent, and C. As I told you, I am applying a sinusoidal waveform. We know a sinusoidal representation is Vi is equal to Vm, that is peak voltage, sin omega t, correct, where omega is the natural frequency. Okay. So, for any given waveform, T decides by the frequency 1 kilohertz, 500 hertz, 10 hertz, how much ever you said, you can decide your time period and substitute to get your sine wave. Having done this, we can assume, so see here the diode, if you see the voltage here, I am applying a positive, see any waveform will have a positive and the negative peak, correct. So, if this kind of a waveform is applied, diode is forward biased for the positive half cycle, correct, positive to positive, negative to negative, that is positive to anode, negative to cathode. So, diode conducts in positive half cycle and diode will be off during the negative half cycle, correct, more obvious, correct. So, whenever I am applying, see I am analyzing it in the different cases. So, whenever I am applying positive half cycle of the input, for any AC signal, positive half cycle is half of its time period, correct. So, total time period is T by 2, correct. So, for the first positive half cycle, that is T by 2, diode is on, correct. When the diode is on, see here, when the diode is on, diode offers lower resistance. So, capacitor charges and completes the path this way, correct. So, when the diode is on, it offers low resistance and capacitor charges. So, I can write the KVL to the circuit like this, correct. So, what is it? Plus Vc, okay. Again, let me write the nomenclatures of voltages, potential, plus minus, minus plus. So, plus Vc, again plus Vk, that is new voltage of diode, minus Vi is equal to 0. This is my KVL, right, applying KVL to this loop. So, let me write it in the fresh page. So, Vc plus Vk minus Vi is equal to 0. Rearranging, Vc is equal to Vi minus Vk. Vi is nothing but Vm minus Vk. This is my equation for reference for positive half cycle. Now, during negative half cycle, what happens? Diode is off, correct. So, diode is off, so that means my capacitance can't continue charging, correct, it can't continue any charging there. So, what it will do, it will instead try discharging. What will happen in the negative half cycle? Diode is off, capacitance start to discharge through resistance. Why? The path offered by diode is high resistance. So, capacitance discharge through resistance, correct. So, it slowly discharge, okay. So, the time period for discharge is again T by 2. Now, let us apply the KVL the same way for the output loop now. So, V out plus Vc minus Vi is equal to 0. V out, I will just rearrange, Vm minus Vc, correct. So, just now we had calculated what is Vc value here. Let us substitute. V out is equal to Vm minus, correct, Vm plus Vk. So, V out is equal to Vk, as good as that, because both of these gets cancelled, correct. V out is equal to Vk. That means my clamping level is at, for silicon diode, V out will be clamped at 0.7 volts. So, you can see here I am getting a positive voltage here. So, hence it is reference is positive peak, correct. Now, let us rewrite the waveform. I am rewriting the waveform now. First, I will write the input sinusoidal. You can take any waveform. I am taking input sinusoidal wave. This is my Vm, minus Vm, 0, correct. So, this is time period. Now, let us fix, as I told you, I have to fix the positive peak because it is a negative clamper. So, I am fixing the positive peak. I am assuming silicon diode. I am fixing the positive peak at 0.7 volt. Now, let us fix my positive peak here. So, rest of the waveform just shifts below. The waveforms looks something like this. If you refer these two signals, you can see the waveform is pushed below. Now, how do I calculate these values, correct? Here blindly we wrote 0.7, I will just fix. Rest of these terminals I will just push it down. Mathematically also I have to calculate these points so that my waveform will be more accurate. How will we do that calculation? Let us see. Okay, first I am substituting. Okay, I am substituting 0 at 0 if my input is at 0, correct. My output will be V out is equal to minus Vm minus Vk. If my input is at, see, if you see the waveform here, input 3, I have to analyze it for 3 different stages, that is input at 0, this point, plus Vm, this is again the same point, this is again the same point, need not calculate, again minus Vm, correct. So, these 3 points if I calculate, I will be able to redraw the waveform neatly, correct. So, here 0 again madidvi, 0 what did we do? Minus Vm minus Vk, I am substituting it for this equation. Remember this equation I am substituting. Okay, now I am substituting, okay, input is plus Vm, correct. V out is equal to Vk. Now, input is at minus Vm, V out is equal to minus Vm minus 2 Vm plus Vk. So, substituting different values, you will be able to get different peaks. Same procedure can be followed for positive clamper also. Here whatever the voltage we get, it is for the negative half cycle, and we push the negative peak with the reference voltage, and rest of the waveform will follow as it is. Hope this video was helpful. It made you people learn about the application of diode being a clamping circuit. I have illustrated one circuit here. You can do the positive clamper on your own. If there are any queries, doubts and more clarity needed, please write to us. Thank you.